Hi, everybody. How you doing?
Hello.
Okay, let's see. All right, all is well. I checked my audio. Seems like we're good. Couple things I wanted to do before I get into. I'm going to go over a problem today, as you know. And the first thing I wanted to do was go over the to-do list and make sure everybody knows what is happening. So let me get queued up for that. Okay, first of all, the quiz I think went like really, really well. I held my breath because I think that I don't love the lockdown browser a lot, and but it's the only thing we've got. And from what I could tell, nobody really had any trouble with it. Did anybody get kicked out of the browser and then have to come back in? Everything went okay? And no problems? It was great because I have to, you were kind of my guinea pigs because I've got to use the browser for IE 380 in a few weeks for their first exam, and there's 350 people in there. I'm sure somebody will have a problem with it, but the fact that you guys had no problems with it was fantastic. Everybody kept their hands on camera. Everything went really, really well. So I was super happy about that. On the to-do list here, just to kind of give you, what's coming up. I like to do that. It's something I would do if I were teaching in front of you live. So this is the week 2 to-do list is where we are right now, but I wanted to kind of foreshadow what's going on next week. There will be, our second homework is going to be due on Monday. I know Monday is a holiday, but I just have it due as Monday. It'd be good if you could get it done by Monday because we're going to have our second quiz on Tuesday the 8th. And all of the information about that quiz is on the quiz 2 information page here. So let's just take a quick look at that. It'll be, the same type of format as quiz 1, 5 to 7 questions. The first question is about, academic integrity. This one will cover everything that we did in week 2, which includes the videos and any of the readings I asked you to do. And this particular today, what I'm going to do in the next hour or so would be something you want to take a look at as well. Same usual rules, same must, mays, and may nots. Just wanted to point that out. And then, so that'll be our second quiz. And then on Thursday, I'm going to do another one of these live things. Now, what I wanted to kind of check out here, I'll send out an email about it, but on Tuesday the 8th, which is when you are going to take your quiz, what I want to try is I went to our actual room, like the room that we would have been in if we were 100% on campus. I went there the other day, and it's a small room in Wexler Hall, which is right across from ECG, and it's I think where most of the like math classes are held. Anyway, it's not a huge room, but it has the capability of a document camera, and I mean I could teach in there. So what I want to do is on Tuesday after the quiz, I'm going to be in that room, okay? And if anybody wants to come, and we'll do like a little pilot test in that room, see if I can get the technology to work. And basically what I'll do on Tuesday the 8th is exactly the same thing that I plan to do on Thursday the 10th on Zoom. Kind of get what I'm saying? Like I'm going to give like the same presentation twice. So if anybody is interested in showing up on Tuesday after the quiz, like around 3:30 at that room, or you could even go to the room and take the quiz in the room if you want to, I don't care. We could try out the technology and see how it goes. And if I like it, then what we could do is try to do a blended class from that day forward. What it looked like, I tried it the other day though, and I couldn't make the document camera get onto the Zoom meeting. So I could have an IT person meet me there Tuesday. Would you unmic yourself if you were interested in doing something like that on Tuesday? I'm gonna be there anyway, but would anybody be in the room after the quiz to just see how it goes? Or have you gotten used to the Zoom, the Zoom classroom now? No interest? All right. Well, I'll send out, I'm probably going to make a Google Doc and I'll have you put a check mark there if you think you want to show up. If nobody's going to show up, then I just won't do it. But I know that some people would like to, start coming back to class. So we'll see. I'm just going to test it out. Any questions about the to-do list before I move forward? Nope. Okay. So I'm unsharing and I'm going to start the recording here. It should be, is it working now? Oh. Okay. Do you guys hear that when she says this meeting is being recorded? Do you hear that? Yes, you do.
Yeah.
Okay. It's so annoying. I don't like it, but it is what it is. Okay. So I am going to switch to my document cam here. Whoops, that's not it. See here. Now what you might want to do, I don't know if you figured this out, I found out that some students don't know how to do this. You don't have to look at a teeny tiny window of what I'm doing. You can go to the upper right corner and you can pin the video if you want to. I don't know if you knew that, but you can make it, be almost full screen or full screen. I think you can do. Okay, this is a problem from the textbook, and I can't remember if I mentioned this in the video or not, but occasionally we can have a mixed random variable where it actually has a discrete component and it also has a continuous component. I don't generally do problems that are like that, but in looking for something interesting to do for today's class, I thought this was kind of interesting and it wasn't terribly difficult to work through, and I decided to do it basically. So what we've got here is a mixed random variable. And this is not exactly the way the book does this problem. I'm kind of attacking it in my own way with my own questions. Because still I feel like we're still in a little bit of a review period here at the beginning of the semester. So here's what we've got. If you can take a look at the diagram there, we have two different buses that B1 and B2, and what they do is as it says, it shuttles passengers between two stations, and they indicate those as S1 and S2. Then they give us some information. One is that X1 and X2 will be the locations of each of the buses. So those are actually going to be random variables. We're using little x and little x1 and little x2 there to denote, a specific spot, but they're actually going to be random variables. And then they give us some other information. They say that each bus is going to behave the same. And each bus is going to spend 25% of its time at station 1 and 25% of its time at station 2. And then the remaining 50% will be between the two stations. So that's what number 2 is there in the information. And they say that the speed of the travel is fixed. So they're assuming that, there's no acceleration or deceleration. It's all the same. Now, if it's spending 50% of its time at between the two stations, that means that a quarter of the time it's spent here going clockwise between S1 and S2, and another quarter of its time is spent going counterclockwise between S2 and S1. So what I thought I could do with this problem is help do a little bit of a review of CDF, because sometimes that still poses some problems for even the most educated of industrial engineering students. So I'm going to denote X as the location of B1. Technically, it should be X1 if I'm following the notes here, so maybe I'll just edit that. So X1 is going to be the location of bus 1. So I'm really just going to deal with bus 1 here with this particular problem. So what I would like you to do is, in reading this problem based on what I just said, and we have a radius of 1 mile, that means that the total track here going between S1, if I go counterclockwise all the way around. It says 2 pi, but it would be 2 pi times the radius. So it's technically 2 pi miles total all the way around because of circumference is 2 pi r, right? So what I want to do right now, and I'm going to pop into them too, is I want to do that breakout room thing again. And what I would like you to do is, with the people in your room, first introduce yourselves and say hello. And what I would like you to do is to fill out this portion right there of this sheet. So just tell me what the CDF would be. And remember that the CDF, again, remember what that is. Technically, it will be of x1. That's going to be the probability that my random variable is less than or equal to a particular value. So technically, that should be x1 right there. And just fill in the blanks here. I'm going to go 10 minutes. And then if you want to, go ahead and move forward, and you can do parts. You can even try to graph it. I'm not asking you to graph it right now. Let's see, we've got 14 people. I think I'm going to make three rooms, and yeah, let's just see how it goes. Move forward if you'd like to, and I will see you back in about 10 minutes or so. 1, 2, 3 rooms manually. Please accept the invitation to the room, okay? No, it says I have to assign it. Wait a second. I don't want to do it. Oh, open all rooms. There we go. Well, hang on a minute. It's giving me a hard time. There we go. Sarvith and Josh, can you join the rooms? Thank you. Okay, I don't know if that was enough time or not. It's hard to tell when we're doing this virtually, but let's see how it went. So tell me, any volunteers at all, what would go right here? So what would the CDF of the location of bus 1 be whenever we have some value of X less than 0? This is an easy one.
0.
Exactly. And then let's do the other easy one. What's the other easy one in this list?
The last one.
Yeah, and what would that be? Right here.
1.
1, exactly. Now there's a couple of other easy ones. So we have this mixed random variable that has a discrete component and a continuous component. So the discrete component is going to occur whenever x is equal to 0 pi. So according to the problem wording, what would this be?
0.25.
I didn't get that. Did anybody get anything else? %25 would be the same as what fraction? 1/4. So right here, because it says 25% of its time at station 1 and then 25% at station 2. And I see that station 2 occurs here at the value of x equals pi. That's 25% there, but we're looking for the CDF here. So we would have spent 1/4 of the time is going to be spent here. And 1/4 of the time is spent here. And then they said that 50% of the time would be spent between the two. So we also know, I'm just going to do it this way. I'll just kind of, I'm going to shade it a bit here. This shading here, that's 1/4 of the time. And then that other arc over here, that's going to be 1/4 of the time that a bus spends. So therefore, what would go right here if I'm looking for the CDF? If I'm right here, sitting right here, right now, what is the probability that my bus location is here or something less than here? What would go here? How many times did I say here? Anybody want to take a stab at it?
3/4.
0.75.
3/4. That's exactly right. That's what I got as well. And now I'll just fill in the rest, and you can see if your numbers matched or not. I did decide though to put all of these values into 16ths because it seemed to work out better for me. So what I'm going to do is I'm going to represent each one of these values in this column here as a certain number of 16ths. So 1/4 will be 4/16, and 3/4 is 12/16. And I mean, obviously 1 is 16/16. I'm just going to leave it that way. But let's go to pi over 2, because pi over 2 would be right there. Now, my CDF at this point, if I'm located right here, and of course I can't be because it's a continuous random variable, but if I'm right here, the CDF here is going to be the 1/4 of a time that I spend here, and then half of the 1/4 of the time that I spend here. On this arc here. I guess stop saying here, my God, it's gonna make me crazy. So at pi over 2, I have 1/4 plus 1/2 of 1/4. And I'm gonna write that down. So we'll have 1/4 plus 1/2 of 1/4. And when you do that, it ends up being 3/8, which I'm going to write as 6/16. Should have given myself a little bit more room. Is there anyone out there who also came up with that number, just so I know I'm not all alone? Just a yes would be great.
Yes.
Yes, somebody did. Awesome. Great. And I can use the same logic if I wanted to flip over on this side. And this would represent, we would have pi, well, this would be 1 1/2 pi, right? Which is 3/2 pi, which would be right about there. And if I follow the same logic and do the same manipulation, I ended up with right here, and hopefully I did not screw this up, 14/16 is what it would end up being. It would be 7/8. And then using the same idea, I'll just do one more and then I'll fill in the rest of it. Let's go to pi over 4. Pi over 4 would be right about there. And that would be 1/4 plus 1/4 of 1/4. And so the CDF at pi over 4, if you represent it in 16ths, will be 5/16. And what you do is you see a nice little semi-pattern evolving here. And so at 3/4 pi, which would be right there, that's going to be 7/16. But then we have a jump. Notice that we go 4/16, 5/16, 6/16, 7/16. Then at pi, we jump right up to 12/16. If I continue with these two empty spots, this will be 13/16, 14/16, and 15/16. And the reason that I did it this way, just to come up with some, I'm looking for specific values because eventually, like now, I want to graph the CDF. And we know that the CDF isn't necessarily going to look like everything we expect. It's going to be kind of weird because it's a mixed random variable. But I think that it's helpful to identify what these values are in this column, and it will help me graph it properly. What I decided to do, and I made my graph here just ever so slightly too small. So what I'm going to do is just add one more. It turns out that I just cut it off just a little too quickly. I'm just going to add one more vertical line here, right there. And I'm gonna graph this CDF, and I'm gonna start at, I'm gonna use this as my origin, and this is going to be my location of the bus, X1 going this way. And I'm just gonna go in quarters of pi here. So I have 0 pi, pi over 4, pi over 2. I mean, that's the same thing as 2 pi over 4, obviously then 3/4 pi, then pi, 5/4, and then this would be 6/4 pi, 7/4, and so on. So I can use, I wanted to get it kind of exactly right here so that it looks good. This one right here, this will be pi over 4, and then here we'll have the 2 pi over 4, and 3 pi over 4, and then 4 pi over 4. And 5 pi over 4.
Sorry, Dr. Chatham, we don't see the down part.
Oh, so sorry. There.
Yeah,
Thank you.
that's perfect.
Thank you. That's perfect. I need you to let me know that. Thank you very much. I moved this time. Now I'm in my kitchen where I really like to work, but the lighting is a little bit weird. 6 pi, 7 pi over 4, and then finally 2 pi. So I'll pause and get a little sip of coffee while you fill out the x-axis. And then the y-axis, well, that's just going to be my CDF of my random variable x1. And we know that the CDF can only be something between 0 and 1. And I decided to go up here in increments of the 16ths. I just thought that it read a little bit better, and I'm going to go in orders of 2. So right here, we're going to have 2/16, and then we're going to go to 4/16, and so on. 8/16, and then 10. And then 16/16 is 1. And just to even this out a little bit, I think I'll color the axes. And the next thing I'm going to do is plot these points, and then we're going to decide exactly what my CDF should actually look like. So let me get a better color here that stands out. I think the orange will stand out pretty nicely. I'm not going to look at the less than 0 pi or bigger than 2 pi just quite yet. But what I'm going to do is I'm going to plot all of these points intermediate in between here. I know that as soon as I get to 0 pi that I'm going to have 4/16. So I do know for sure that this is a point right here that lies on the curve that is going to be my CDF for sure. Then I'm going to go up to pi over 4, and I can see that that's going to be 5/16. So that will just be right there. And it's going to work out to be a pretty nice looking little straight line for a time. Then the next is going to be 6/16. That's at pi over 2. And then 7/16. But then it doesn't go to 8/16. Once we get to pi, my CDF now has jumped up to 12/16. So right up here, we have a little bit of a disconnect. It's going to go right there. Then 13/16 and so on. Now it looks pretty again. And then at, let's see, 3.5 pi, we're at 14/16. And then 15/16. And then 1. Okay. To graph the CDF then, because I have this weird mixed random variable, now what I'm going to do is, should I use the orange? I'll continue to use the orange. That's fine. We know that the CDF for any value of x below 0, but not including 0, so I'm going to put a circle right there, will be 0, just like that. So it'll go forever. So if I pick any negative value of pi, I can't possibly have a location of my bus be a negative value of pi. But as soon as I get to 0, because I have this discrete component of this random variable, I do jump up to 4/16 right there. Then for the bus being between S1 and S2, now I have a continuous random variable again. And that continuous random variable means that my CDF actually will lie on this line right here. And in fact, it's going to stay right on that line until it gets to station 2, which is where x1 equals pi. And as soon as it gets there, right, draw a straight line, Linda, right to about here, then it's going to hop right up again. And then we're going to have the same situation. Now, for anything in that region between S2 and S1, my CDF is going to look like this. And as soon as we get to 2 pi, we'll basically be instantaneously back at station 1. And at that point, my CDF will be 1 forever. Now I want to pause here and answer any questions that folks might have, because this is just a graph of it. What I'm going to put over here are the actual equations that represent these 1, 2, 3, 4 pieces. Can I answer any questions right now? All right. Over here then, let's put it all together into something prettier. My CDF at x1 is going to be equal to 0 whenever the location of my bus is less than 0. And then it's going to equal exactly 1/4 when my bus is at 0. Now, between 0 and pi, and not including either one of them in that case. So for anything between S1 and S2, but not at station 1 or station 2, I need to know what the equation of this line is right here. And I can get the equation of that line by using y equals mx plus b, and it's pretty easy to read right off here. If I use right here, you know, the old y equals slope times x plus the y-intercept, we can see that, well, what is y here? Y is going to be my f of x1. And then my slope m is going to be the rise. And I'm just going to take I'm going to take just these 2 points here. Let me see right here. Let's do the slope for these points here because that gets a little messy. So the rise here is going to be 2/16 over the run, which is going to be pi over 2. And when you do that, you're going to end up with that the slope is 1 over 4 pi times x. Does everybody see that? If I do rise over the run, it works out to be the fraction 1 over 4 pi. I would have 2/16 here divided by pi over does that work out? Pi over 2. Yes. All right, and then my y-intercept here will just be 4/16, and that will be the same thing as 1/4. All I've done here is try to figure out what my linear equation is right there. And that will represent what my CDF is going to be between, but not including pi, and 0. And then I'll write that as, so that would be x over 4 pi plus 1/4. Then when we get to pi, which is station 2, so when x is actually equal to pi, that's the other discrete component of this weird random variable. That's going to be 3/4 right there. And then here we've got to be a little bit careful. I mean, we can go ahead and project. I guess you could probably, if you did a very, very good diagram, you would be able to just kind of use a straight edge here and be able to see that the y-intercept actually is intercepted here at f of x is, the y-intercept is 8/16 or 1/2. Or you could just prove it that way. You could just do it that way by plugging in any one of these points and trying to figure out what the y-intercept is. So you should be able to show that the equation here, and I'll let you determine that. But here again, if I use my y equals mx plus b form, I'm going to see that f of x1, it's going to have the same slope, but it's going to have a different y-intercept. It will be 1 over 4 pi times x, and then the intercept though this time is going to be 1/2. And a way that you could have gotten the intercept, and maybe I probably should slow down a little bit and show how I got that, is how did we get this intercept? Let me highlight it right here. How do we know this? It's probably been a while since you did a bunch of geometry. Let me just kind of show you how I got it up here in yellow. All I'm going to do is take a point that I know for sure lies on this line. So let's just take the point pi. We know this point here, pi and 12/16. 12/16. So I'm going to take the point pi and 12 over 16, and I'm going to plug that into the y equals mx plus b formula. So what would that actually look like? That would be then y is 12/16 equals, now the slope here, you can pretty easily see that the slope again ends up being 1 over 4 pi, because we do the same thing. We've got a rise of 2/16 over a run of pi over 2 here. So we can see that that would be 1 over 4 pi times x in this case, plus, and then this is the y-intercept. Let me see if I'm running out of space here. That's not too bad. And so when you solve for this, you can see that b is going to end up being 1/2, and that's where I got that 1/2 from. So I just wanted to point that out. I had to remember a little bit how to do that myself. So now I've got the third piece of my CDF, and that is going to be for x1 now is going to be between pi, but not including pi, and all the way up to 2 pi, but not including 2 pi. And that equation is, well, what I just came up with over here. That's going to be x over 4 pi. But this time it'll be plus 1/2. And then finally, my CDF is going to be equal to 1 whenever the location of my bus is, well, we'll just say bigger than or equal to 2 pi. It actually just, you know, repeats itself, but you get the idea. All right, that's the first part. And I just thought this was instructive because it helps us, it's a little bit of a deeper dive into a little bit more complex variable, but it also helps us remember what a CDF is and the fact that it has to, you know, be bordered by 0 and 1 and so on. So that was part A, which was to determine and graph the CDF of X. And by the determine part, we used this piece to get to this piece. So determine, this was the determine part that I was looking for. It needs to be in these nice equations and fully defined, you know, with the bookends of the 0 and the 1. Now let's take it one step further. Now that we've got the CDF right here, what I'm going to do, and I just repeated the problem, now I'm going to do parts B and C. And part B and C ask me to figure out what the probability distribution of X is and to graph it. And I don't know if I want to graph it. I'll let you graph it because it's easy to do. I can graph it, it's fine. And then it says determine the expected location of B1. So remember that I edited this a little bit. So this is actually random variable X1. And unfortunately, some of my work just bled through, so kind of ignore that. This is what my CDF looks like, and I'm just going to fill in the blanks from what I just did. So we had 0 here, 1/4 here, then we had X over 4 pi plus 1/4, and then we had X over 4 pi, it should be X1, darn it, X1, these are all little X1s because I meant to be consistent with the problem, these are all little X1s. And then X1 over 4 pi, and this is plus 1/2 right there. Now, for a continuous random variable, does anyone remember how we go from a CDF to a PDF? And I specifically said the probability distribution because it is a mixed random variable, so I really couldn't say PMF, and I really couldn't say PDF. So instead, I said the probability distribution of X1. So let me get you started out here. I'm going to use a scripted F here because I have, I think, well, I've got half and half really of continuous and discrete, but let's just identify it this way. So little f of X1, that is going to be equal to exactly 1/4 when X1 is equal to 0. And then tell me, what will it be for this piece right here when X1 is between 0 and pi? What will go right there? How do we go from, what do we do to a CDF if we want to get a PDF for a continuous random variable? What do I have to do to this? Surely someone knows.
Integrate?
Well, if we would integrate this to get the CDF, what would I do the opposite? Somebody knows, come on. what do I have to do to this to get, to get a, to get a, hang on. If I go from my lowest value of X to a general X over a PDF, that gets me a CDF. But if I want to go the other way, how do I get a CDF? How do I get a PDF from a CDF? What would I have to do?
Take the
Differentiate.
derivative.
Right, the first derivative, exactly. So therefore, if I take the first derivative for my x1 between 0 and pi, I'm just going to get 1 over 4 pi here. And then when x is equal to pi, it's not going to be 3/4 pi. It's going to be the 3/4 pi minus this quarter minus that quarter. So it would be 1/4 right here. And that's not necessarily that easy to see. And then same thing here for pi less than x1 less than 2 pi. We're going to end up with the first derivative of this piece right here, 1 over 4 pi. And so this is part B. This is the probability distribution of x1. And if I wanted to graph it, and I forgot to do that in part of my preparation, but I think we can do it this way. Let's see, 1 over 4 pi is going to be technically, it's going to be weird looking. You're just going to have blades of grass at some point here, and then you're going to have a constant somewhere else. And I might get these two mixed up depending on how you decide to look at pi in radians or in degrees. So we would actually have at x1 here, we're going to go from 0 up to, let's see, pi up to 2 pi. And if we had to plot this at 0 and at pi, we would have the height here at 1/4. Here. And where is it at pi? Right there. And then I might have this, it might be below or above. I actually didn't think about it that hard, but we'd have another 4 pi here. And then for that continuous piece between, it would be like this, and then like this. And then again, like, but there would be that hole right there, right at 0 and pi. I kind of regret having said graph it, so ignore that. It's kind of messy and ugly. I regret that. Now, how would I get the expected location of B1? C is just code for find the expected value of x1, right? So how would we get that? Well, for the, if we had had, let me move over here. If we had had x being a discrete random variable, so if x is discrete, then the expected value of x would be, we sum over all of my values of x and take x times its probability mass function. If x is continuous, then the expected value of x, we take the integral over all x and take x times, is it there better? There we go. Dx, there we go. So to get the expected position of bus 1, I'm actually going to have to do both of these. And I think I will. So we'll start out with this piece right here is discrete. So we would have a 0 times 1/4 plus, now for this piece is continuous. So now I'm going to integrate from x1 going from 0 to pi over, and I have to throw an x1 in here, x1 times its PDF right there over 4 pi dx1. Then we have another discrete piece here, so that would be 1/4. I'm sorry, let me be consistent. Pi times 1/4. And then we would have an integral from x1 going from pi to 2 pi over x1 divided by 4 pi dx1. And I do not think I actually did this, so I'm going to do this real quickly. You guys do it, I'll do it. Let's make sure we all get the same value. All right. So that. Let me see. I don't think it's going to be a surprise what it is, but I did it really fast and got 3/4 pi. Did anybody else get that? No takers? I got this piece right here. Right here. I got that would be pi squared over 8 pi, so that ends up being pi over 8. And then this is pi over 4, obviously. And then here, we get x1 squared over 8 pi. So we'd have 4 pi squared minus 3 pi squared. So I got that this was 3 pi over 8. Does anybody give me an amen on these? You're good with that? No? All right. So we have pi over 2 plus pi over 4. So I get 3 pi over 4. I'm pretty sure that's right. Anyway, that was my little exercise for today, and I thought that it would be, I don't know, a good little problem to remind us of what things are. And also an upcoming homework number 3, I have the same diagram, but I actually ask you to make some different assumptions, and the homework problem is actually much easier than what this is. So I guess my goal is, with these live sessions that I'm doing, I want them to be a little bit more challenging types of problems that we can go through a little bit slower. And the homework shouldn't be horrible, but there should be some problems that are a little bit challenging for us. And I do find these problems challenging myself because if you look at some of the problems in the book, I don't even attempt them because they just take a really, really long time. So Anyway, can I answer any questions right now? Because this was really where I wanted to stop for today. Nothing? All right. Okay, folks, then I'm going to sign off. I'll stay and wait in the room here if anybody has any residual questions, but we will be in touch. All right. Have a nice day.
Thank you.
Thank you.
Bye.
I'm going to stop the recording right now. Yeah. There we go.